Hi there, and welcome to another lecture of CSE331. In today's video, we're going to learn some formal notations and definitions relating to finite automata. We can formally define a finite automaton or a finite state machine as a model that can recognize patterns of strings over an alphabet. It can either accept or reject an input depending on whether the input matches the pattern that's defined by the automaton or not. While processing an input string, if it reaches a final state, then the string is accepted, otherwise it's rejected. Let's look at the example from our last video to explain what I really mean. In our buzzer quiz example, we had two final or accepting states. Team A wins and Team B wins were the two final states. Now, we haven't really learned what it really means to be the final state, but we will learn that soon. For now, let's say I made up a condition for this quiz that one of the teams must end up winning. Otherwise, any input that wouldn't lead to one of these two states, which I'm calling the final states, wouldn't be valid. The string that we processed, this string here, at the end of the processing, it did end up in one of the final states. We did reach the state called Team A wins. So the string is accepted. If it ended up in any other states other than these two here, the string would be rejected. Now, if I give you an input string, this one, ABB, AAB, can you figure out whether it would be accepted or rejected by this automaton? Now, let's go over some more formal definitions, and you'll already know about some of these. An alphabet is a finite set of symbols. Two of the most common alphabets that we work with are ASCII and Unicode. But it can be as small as a binary alphabet that consists of only 0 and 1. We will be using the binary alphabet a lot in this course. But it's important to remember that an alphabet can be a set of any number and type of symbols. It is, however, a finite set. In our previous buzzer quiz example, the alphabet that we worked with contained A, B, and N. Now, what is the language of a finite automaton? The job of any automaton is to define a language. The language of an automaton is a set of strings that are accepted by that automaton. That means if we process those strings that belong in the language of an automaton, it will end up in a final state. The notation that represents the language of an automaton is L of A, where A is the automaton, and L, as you can guess, stands for language. And we're back to the same example. In the last video, we processed this specific string here, which led us to the state Team A wins. And it's one of the two final states, as we discussed earlier. That means the string, since it did end up being in one of the two final states, it does belong in the language that is defined by this automaton. Now, here's a little something for you. Let's call this automaton A. I'm just denoting it with A. Given the strings W1 and W2, can you find out whether they belong in the language of A or not? And by the way, these are just some set notations that I'm using here. And try to figure out one more thing. Can you describe in human terms what it really means um, to be in the language of this automaton? What kind of strings does this automaton accept? Finite automata can be of two types: deterministic finite automata, or DFA in short, or non-deterministic finite automata, in short, NFA. But in this video, we're only going to focus on DFAs. A deterministic finite automata, or DFA, is represented by a 5-tuple, meaning that it consists of 5 things: a finite set of states that is denoted by Q, an alphabet or a finite set of symbols which is traditionally represented by sigma. The inputs will consist of symbols from the alphabet the automaton is defined for. It has a transition function that dictates how the automaton moves from one state to another in response to an input. The symbol we represent it with is delta. We're going to discuss a lot about this transition function soon. One of the states in Q is the designated start state, and we usually name it Q sub 0. And some of the states are designated as final or accepting states. There can be multiple final states in an automaton. The set of final states is denoted by F, and it's a subset of Q. Note that Q0 is just one state. It's the starting state. But since there can be multiple final states, we represent it as a set. The transition function delta takes in 2 arguments or parameters. The first one is a state, and the second one is an input symbol. As the output of the function, it tells you the state that the automaton moves to when it is in state Q, and the next input symbol is A. Here, Q is a state, the first argument, and A is an input symbol, the second argument. In this representation here, if the current state is Q sub I and the next input symbol is A, then the automaton moves to state Q sub J. In the buzzer quiz example, delta of 0, 0 and A results in the state 2, 0. Means that if you're in state 0, 0 and the next input symbol is A, then the automaton should move to state 2, 0. Can you tell me what delta of 0, 0 and B should be? Where should it lead to? What would be the answer? Let's see if we can find it out. For a running example, let's take this automaton. We're going to try and design an automaton to accept all binary strings that contain 2 consecutive 1s, or 1, 1 as a substring. The state Q sub 0 is the starting state. This state means that we haven't seen anything and definitely no 1s yet. As long as the next input is 0, it stays in the same state. The automaton moves to state Q1 when the next input symbol is 1. This state means that it saw the first one of the substring 1, 1. Alternatively, we can say that if the automaton is in state Q1, it means that the last input symbol was 1, that we have made progress towards seeing 2 consecutive 1s. It has seen the first one of 2 consecutive 1s, and if the next symbol is also a 1, then it'll be a success. But what should happen if the automaton is at Q1 and the next input is 0? Remember, this state means that the last symbol was 1. So if the next symbol is 0, we should go back to the state where we haven't made any progress towards seeing 2 consecutive ones. That would be the start state Q0. Now, if it's at state Q1, which means the last symbol was 1, and if the next symbol is also 1, that means the input contains 2 consecutive ones, and it moves to state Q2. Since this automaton should accept strings that contain 2 consecutive ones, Q2 is the final state. That's why we use the double circle here. Now, if the automaton is at Q2, or the final state, it means that it has seen 2 consecutive ones. There's no other way it could have gotten there. Once it has seen 1, 1 in the input string, the condition is already fulfilled. The string belongs in the language of this automaton. So no matter what the remaining input symbols are, it should stay in the accepting state Q2. I'm just marking what each state means here for your convenience. This is how we can represent an automaton as a graph. The nodes or the vertices are the states. The edges or arcs labeled with the input symbols show the transitions on those symbols from those states. The start state is labeled with an arrow and the word start. And the final states are indicated by double circles. The set Q for this automaton contains the states Q0, Q1, and Q2, because Q is the set of states. We're concerned with binary strings here, so the alphabet contains 0 and 1. The start state is Q0, and the set of final states, F, has only one element for this automaton, and that is Q2. This automaton here is a deterministic finite automaton, or a DFA. What makes it a DFA is its transition function delta. Delta of Q0 and 0 is Q0, as we can see from this loop transition here. And delta of Q0 and 1 is Q1, which means that when the automaton is at the state Q0, on seeing the symbol 1, it should move to the state Q1. And we can calculate the rest of the deltas in the same way. Basically, this is a DFA because of the fact that there is only one transition from each state on one specific symbol. For a single input symbol, a DFA cannot have more than one transitions. It cannot have transitions to 2 different states for one single symbol. As you can see here, the output of a transition function is just one single state. Every transition function returns just one state. The automaton cannot be in 2 different states at any given moment. That's why we call it deterministic. We can also represent it as a table where the rows correspond to the states of the automaton, and the columns correspond to the input symbols of the alphabet. We indicate the final state by putting a star next to its name, and we indicate the start state by an arrow. The entries of the table are the output of the transition function delta when applied on the state of the corresponding row and the input symbol of the corresponding column. Let's take the first row for an example. When the automaton is in state Q0 and the next symbol is 0, it should stay in the state Q0. So in the cell that corresponds to the state Q0 and the input symbol 0, we write Q0. If the next symbol is 1, it should move to state Q1. So the cell corresponding to the state Q0 and the symbol 1 contains Q1. And we can similarly fill up the rest of the table. Now before ending this video, I'd like you to know some conventions that we're going to follow. We're going to use the letters at the end of the alphabet, like W, X, Y, Z, and sometimes we're going to use U and V to represent strings. And we're going to use the letters at the beginning of the alphabet to represent a single symbol. So whenever you see W, you'll be like, hey, that's a string, even if I don't explicitly mention it. That's it for today's video, and I'll see you in the next one.